We're looking at solving systems of equations, and we've done that with the elimination method and the substitution method. We're now going to use a method using matrices to help us solve these systems of equations. So let's just define what a matrix is. Matrices is just plural for matrix. So let's define what a matrix is first. So definition of a matrix, all it is a rectangular array of real numbers. We have m rows and n columns in this case. We always name it with a capital letter. And the first subscript is the row and the second subscript is the column. So you really don't need to know too much about this to be able to use matrices to solve our systems of equation. But for instance, right here, this says A13. This means that this is the element in the first row, third column. Row 1, first row. This is column 1, column 2, column 3, third column. So again, you don't really need to know a lot of that terminology. All we need to know really is if we have this system of equations, let me just pull one up really quickly. If we have the systems of equations, so let's say we have, and it's asking us to solve the system 5x minus 2y plus z equals 11. 2x plus y plus 3z equals 0. And last equation is 6x minus 2y minus 2z equals 16. In the last class I mentioned it's really important to make sure that you wrote down the equation right. It's also important when we're doing this that we specify what we're doing. Because if we make a little teeny error, sometimes it can be kind of tedious to find. And so listing the steps that we're doing is going to be helpful to find those errors. And then I found that a lot of times the error comes from not writing the equation down right. So I just always tend to check just to make sure. So I'm just going to rewrite it off and make sure I wrote it down right. So 5x minus 2y plus 7 equals 11. 2x plus y plus 3z equals 0. 6x minus 2y minus 2z equals 16. Okay, good to go. So first thing that we want to do is we want to take our systems of equations and we're going to rewrite this as a matrix. And what we're doing is that first row of our matrix, all it is the coefficients. And then we're going to do a vertical line and then that constant that is on the other side of the equal sign. So for instance, this matrix right here, my first row, I'm going to have a 5, -2, 1. The equal sign is here, so I'm going to put the vertical line, 11. So that's the first row of this matrix. So my second row, so again, just the coefficients. So I have 2, 1, 3, and then 0. The third row would be 6, -2, -2, 16. Okay, so that's the first step that we would do when we need to solve these systems of equations, or we want to solve them using matrices. Actually, the first thing you want to do if your equations are not in standard form, this is in standard form where all the variables are on the left and the constant is on the right. That's actually what we would do if it's not in that form. Okay, so there's certain operations that we can perform on matrices or a matrix or a system of equations to perform an equivalent solution at the end. So let me give you the row operations. So these are all the things that we can do to give us an equivalent system. So let me just kind of read through and talk this out. So elementary row operations, that's what we're performing, are operations that can be performed on a matrix that will produce a row equivalent matrix. If the matrix is an augmented matrix constructed from a system of linear equations, then the row equivalent matrix will have the same solution set as the original matrix. Okay, so these are the operations that we can perform to get an equivalent, a matrix with the same solutions as the original. So we're working with a system of linear equations. There are 3 operations you could perform, which would not change our solution set. So first thing that we can do, and it's not in any order that we can do these, and we can do them in any order we want. We can interchange 2 equations. So I could rewrite equation 1 as equation 2 and equation 2 as equation 1, and that's not going to change my solution set. And I'm going to say we're going to interchange 2 rows for our matrix. So swapping rows in this matrix is not going to affect my solution. We can multiply any row by a non-zero constant. And then the last thing that we can do, we can multiply an equation by a non-zero constant and then add it to another equation, replacing one of those equations. Okay, so when the system of linear equations is converted into an augmented matrix, each equation becomes a row. So there are now 3 elementary row operations which are produced for the row equivalent matrix. Okay, so the first thing was talking about if we just had a system of equations and we hadn't written it as a matrix. Now, if we think of it and we write it as a matrix, these are the following things that we can do. We can interchange a row. That's just like interchanging an equation. We can multiply a row by a non-zero constant. That's the same thing as multiplying an equation by a non-zero constant. And we can multiply a row by a non-zero constant and add it to another row, replacing that row. Okay. And we had talked about those operations in our last class period. I don't want to get too caught up in this, but this is basically what we're doing. We're trying to get our matrix in this form. Let me show you what we're trying to do. So we're going to try to take this matrix here, and we're going to do those operations. And our goal is to get this down to look like the following. There's 2 ways that we can do it. If we can, and it's not too hard, what we want to do is we want to get a 1. In this case, it would be 1, 0, 0. We'd have this vertical line and we'd get some number over here, and let's just call it A. We would want to get the second row as 0, 1, 0. Let's call that equals, let's say that was constant was B, and 0, 0, 1, C. If that's the case, notice that the coefficients for our first column, those were coefficients for X. Second column was Y. Z equals our answer, or our constant. And so if we can manipulate our matrix to get into this form, notice we can read off our solution. So this is X, Y, Z equals some number. And so this first row, I have 1X. So X plus 0Y plus 0Z, I normally wouldn't write those zeros in there, equals A. So this is saying that X then is A. My second row would say 0x plus 1y, or y, plus 0z is equal to b. So I know that in this case, for that equation, y is b. And then the last equation, I can also read off that solution. I would get 0x plus 0y plus z. So z is equal to c. So if we can manipulate our matrix to look like that, we can just read off our solution. Sometimes it's hard to get it that way. We'll get into, and I tried my hardest not to deal with fractions if we can manipulate it and work with it and not to do that. But sometimes you get some nasty fractions in there. And so if we can somehow just get this lower half, and we call this ones here, this is ones in our main diagonal. So if we can get that lower half to be all zeros, then we can figure out what z is. And then we can back substitute. Once we know what z is, we could plug it in here and figure out what y is and back substitute. So that's another way that we might look at it, depending on our system. So we talked about what types of systems that we could have in the last class. And so we have three different types of systems of equations. We could have one that has one solution. And so I'm just going to go through really quickly the different types of solutions you can get while you're solving a system of equations and what it would look like if it was in a matrix form while we were solving. So there's three different types of solutions which are possible when solving equations. That first one is an independent. The system is consistent. It's a unique solution. The row reduced echelon form has the same number of zeros as rows as variables. And the left-hand side is usually the identity matrix, but not necessarily. This matrix with ones in the main diagonal and zeros above and below those ones, that is the identity matrix. But again, you really don't need to know that to be solving these. There must be at least as many equations as variables to get an independent system. So let's say we had equations with three variables, x, y, and z, and we only had two equations. There's less equations than variables, so this wouldn't be an independent system. It couldn't be. In order to be independent, we have to have the same number, at least the same number of equations as variables. So looking at this matrix, let's say that you had did all your work using those row operations and you converted your matrix to look like this. And then, like I had showed you before, we can read off our solution, right? Because this is 1x plus 0y plus 0z equals 3. So x is 3. Second equation is 0x plus 1y plus 0z equals 1. So we get y equals 1. And the last one, 0x plus 0y plus z equals 2. So z is 2. Okay, so if we get numbers like that for our variables, then we know it's independent and it only has one solution. But let's say you're working through your matrix and you're using your row operations and you get something like this where you have a row of all zeros. This is a dependent system. If we were talking about just lines, an equation with two variables, they would be lines that are lying on top of each other. And so every point on the line would be a point on the system or a solution to that system. Okay, so this is a consistent system because it has at least one solution. It has many solutions, actually infinite. Write the answer in parametric form, and I'll tell you what that means in a minute. A row reduced matrix has more variables than non-zero rows. And there doesn't have to be any row of zeros, but there usually is. And there could happen when there is less equations than variables. This can happen. Okay, so let's read through each row of this matrix and rewrite it as an equation. So this is saying 1x or x plus 0y, so I don't have to write that, plus 3z is equal to 4. My second row, if I rewrote that as an equation, is 0x plus 1y minus 2z is equal to 3. And I'm not going to write the last row because those are all just 0. 0 equals 0. So what we want to do here is we want to rewrite each variable in terms of 1. And so here, let's solve for y. So let's get y by itself. So we could get here that y is equal to, adding 2z to both sides, 2z plus 3. Okay, so here's y in terms of z, and now we want to get x in terms of z. And so we can also do that in here by, let's solve for x. And so that first equation, I can get x by itself by subtracting 3z. So I get x is equal to negative 3z plus 4. So notice that x is in terms of z and y is in terms of z. So our system is dependent, in this case, and how we wrote it, what we choose z to be. And so our solution, our x value is negative 3z plus 4. Our y value is 2z plus 3. And then we have z. So it depends on what we chose z to be or choose z to be. That will give us a solution. So for instance, if we chose z to equal 0, one of our solutions would be our x value would be 4 there, our y value would be 3, and z is 0. Where if we chose z to equal 1, and we went in here and plugged in 1 wherever we saw a z, we would get our x value, our y value, and then z is 1. So plugging in 1 wherever we see a z, we get negative 3 times 1, negative 3 plus 4, so that's 1. 2 times 1 plus 3, so that gives me 5, comma 1. So you can see there's an infinite number of solutions that can happen, and it's, in this case, dependent on what we choose z to be. Okay, so if you get a row of all zeros, then it's probably a dependent system. The last case scenario or type of solution that you can get is an inconsistent system. An inconsistent system has no solutions. If we were to work through the row operations, where you're going to get a row of all zeros, except for the last number isn't 0. So we'll notice that we have in that last row, third row, 0, 0, 0, and then this is equal to 2. And so that's impossible. 0x plus 0y plus 0z equals 2. That's telling me that 0 is equal to 2, and this is false. So if you ever get anything like that, you can stop right there, and there is no solution. And there's different ways to write that. I would just probably say no solution, but you can write the null set. That 0 kind of with a line slash through it is the empty set. Or you can make a set notation as those curly brackets with nothing in it. Again, I would just say no solution there. Okay, so you kind of got down the terminology. Let's start going through this. And so we had started with just setting up a system as a matrix. Let's see if I can find it. Here it is. Okay, so we always want to work column to column. I always work for the farthest left column, this column. And I want to get a 1 in that main diagonal, and I want to get zeros below that for this first column. So there are a couple ways I can do this. I could multiply my row 1 by 1/5. That would make a 1 here if I multiplied by 1/5. The problem is then I have to multiply every single number in that row by 1/5, and that would give me some fractions. And I don't want to deal with fractions if I don't have to. So I wouldn't probably do that. So I would think, because I don't see any ones, if any of these numbers in that first column were 1, I would swap my rows, but none of those are 1, so I can't do that. So I see a couple ways that I can get that first number in that first row, first column, a 1. I could multiply that second row by -2. If I multiply this by -2, that would give me a -4 here, and I know -4 plus that 5 is going to give me a 1. So that's one way to do it. So you can see that there's going to be many ways that you can approach this, but at the end we'll get the same solution. I also see that if I take my row 1, 5, take a negative row 1 and add it to row 3. So that would be -5 plus 6 would also give me a 1. Okay, so either of those methods would work to make that a 1. I'm going to do, how about -2, row 2 plus row 1. For me, I always put the second row that I'm in here with my sum or whatever, that's the one I'm changing. So in here, I'm changing row 1. I'm just using row 2 to manipulate row 1 to look like I want. And so a lot of times what I'll do is I will write down the rows that I haven't changed or I'm not changing yet. So row 2, I'm going to rewrite down because I'm just using it. I'm not changing it. So 2, 1, 3, and then 0. That third row, I'm not changing yet. So let's just rewrite it. 6, -2, -2, 16. Okay, so this is where using matrices versus keeping our system as equations is helpful. Because we don't have to go through and rewrite everything down and sum those equations. It's just a lot less work or a lot cleaner. And so we're taking -2 times this 2. So that's -4. And then -4 plus 5 is 1. So -2 times 1. -2 times 1 is -2 plus the number above -2 gives us -4. -2 times 3 is -6, but if I add that to 1, that would give me a -5. -2 times 0, that's 0, and 0 plus 11 is 11. Okay, so I've just manipulated that first row to have a 1 in that entry that I want. So now I'm going to use that 1 in that column to get rid of the numbers above or below. In this case, there's no numbers above. And so I think to ourselves, what can we multiply this row 1 by so that if I add it to this row 2, that 2 would go to 0? Well, we can multiply this row 1 by -2. So let's do -2, row 1 plus row 2. So row 1 is staying the same. I'm just changing row 2 right now. So I'm going to rewrite row 1 as 1, -4, -5, 11. I'm changing row 2. So -2 times 1 is -2 plus 2 is 0. -2 times -4 is 8. 8 plus 1 is 9. -2 times 5 is -5 is 10. 10 plus 3 is 13. -2 times 11 is -22, and -22 plus 0 is -22. Okay, so we got the 0 where we wanted it in that column. And now we're going to look at getting rid of this 6 down here. So we want this 6 right here to be a 0. And so again, we're going to use the 1 to make that a 0. So if we do -6 row 1 now and add it to row 3, we're changing our row 3. Please stop me if you see me make a arithmetic error, because it will be hard for us to find it. Hopefully I don't do that though. So -6 times 1 is -6. -6 plus this 6 down here is 0. -6 times this -4 is 24. 24 minus 2. Okay, so 24 minus 2 is 22. So I have -6 times this -5, that's 30. 30 minus 2 is 28. And then I have -6 times 11 is -66. -66 plus 16 is 50. And it's -50. Okay, this is where, yuck. This is where I got that first column how I want it, and I want to look at my second column, and I want to get that 1 where that 9 is. So like I said, I want to make this 9 a 1. Thing is, I could multiply that row 2 by 1/9, but then I get a 13/9 and a -22/9. And then when I have to start adding things to different rows, it just gets so ugly. And I'm thinking to myself, what can I do to make that 9 a 1? I can't use that a row 1 here, because if I use that in row 1, because I noticed 2 times row 1, that would be -8. -8 plus 9 is 1. The problem is if I did that, then this 0 we just made would now become a different number other than 0. So I don't want to do that. So I was looking at the number below that 9, which is a 22. I know if I add some multiple of 9 to 22, that's not going to give me 1. But then I noticed that, well, 2 times 22 is 44. And I know 9 times 5 is 45. So if I have a -44 and a +45, that would give me 1. So I'm going to do some, make this a little easier by, let's do, so we're doing -2 row 3. And we're going to add it to 5 times row 2. So let me rewrite my row 1, because I'm not changing that. 1, -4, -5, and 11. I'm not changing my row 3. So I have 0, 22, 28, and 50. So that first entry is not going to change because 0 times anything is 0, plus this 0 above is 0. Our whole point to multiply this by -2 was to get -44 plus 5 times 9. So that's going to give us a 1 here. We know that's a 1. So we need -2 times 28. Which is -56, and we're adding that to 5 times 13. So we're going to get back 9 here. And now we're going to do -2 times 50, that's 100, and 100 times 5 times -22. So 100 plus 5 times -22. And that's going to give us -10. So we got that 1 where we wanted it. And so now we're going to use that row 2 to get rid of the number above and below that 1. So working with column 2 now. to manipulate it. So if we multiply row 2 by 4 and we add it to row 1. So the only row I'm not changing right now is going to be my row 2. So I'm going to just rewrite it 0, 1, 9, negative 10. Okay, so 4 times 1 is 4. I'm sorry, 4 times 0 is 0 plus 1 is 1. 4 times 1 is 4 minus 4 is 0. 4 times 9 is 36. 36 minus 5 is 31. 4 times negative 10 is negative 40. Negative 40 plus 11 is negative 29. So now let's make this 22 here a 0. So we're going to do negative 22, row 2 plus row 3. So negative 22 times 0 is 0 plus 0 is 0. Negative 22 times 0 is negative 22 plus 22 is 0. So negative 22 times 9. So that's negative 198 plus 28. That gives us a negative 170. Okay, so negative 22 times negative 10. And then we're going to add that, which is 220 times row 3, which is 50, which is 270. I did something wrong. Right here. This should have been a negative 50 right here. This should be a negative 50 right here. So negative 22 times negative 10, that's, sorry, let's just do that again. That's negative 220, negative 220 plus negative 50. Actually, positive 220 minus 50, that's better, is 170. Okay, so that third row, third column, because we got the first column how we want it, we got the second column how we want it, we're now going to the third column. And this third column, again, we're going to try to first make that 1 where we want it in that main diagonal. And so notice that we could divide every entry in row 3 by negative 170. So let's multiply, or same thing as multiplying by negative 1 over 170 times row 3. So row 1 is the same. Row 2 is the same. Or just changing row 3. So our new row 3 is 0, 0, 1, and 170 times negative 1 over 170 is negative 1. This is where you can stop and you can start doing back substitution. I'm just going to finish it. And so all we now need to do is get the entries above this one to be a 0. So if we do 31 times, or negative 31 row 3 plus row 1, that would make this a 1 in here. So negative 31 times 0, 0. Plus 1 is 1. 0 times anything is 0 plus 0 is 0. Negative 31 times 1 is negative 31 plus 31 is 0. Negative 31 times negative 1 is 31. 31 minus 29 is 2. Now let's look at getting rid of this 9. So if we use the third row, we could do -9 row 3 plus row 2. So 0, 1. So -9 times 1 is -9 plus 9 is 0. -9 times -1 is 9. 9 minus 10 is -1. And then that last row didn't change. 0, 0, 1, -1. Okay, so in here, we just manipulated it that we could just read off the solution. And so we have 1x plus 0y plus 0z equals 2. So we get x equals 2. We have 0x plus 1y plus 0z equals -1. So we get y equals -1. 0x plus 0y plus 1z equals -1. So z is -1. So we can write that as an ordered point. So this is 2, -1, -1. Some of your homework questions just might ask you, is this a solution to our system? And if it was a solution to our system, it would have to work. If we plugged in our values for x, y, and z for each equation, that should come out a true statement. So if I plug in 2 for x, I get 10 for the first equation, minus 2 times -1, so plus 2, minus 1, is that equal to 11? And it is. If I plugged it into my second equation, 2 times 2, that's 4, plus a -1, so minus 1, plus 3 times -1, so minus 3, is that equal to 0? And it is. Last one. 6 times 2 is 12. 12, -2 times -1, so plus 2. -2 times -1, so plus 2. Is that equal to 16? And it is. So when you are checking to see if something is a solution, it has to work for all of the equations in the system. If for some reason it doesn't work for one of them, then you can stop and just say that there's no solution. So our next system of equation that we're going to look at is the following. So we have 3y equals -9z. Second equation, we have 4x plus 2y minus 2z equals 0. And last equation is -3x minus y plus 4z equals -2. Okay, so just again, make sure that you wrote it down right. 3y equals, and I just noticed I did not. This should be equal -9z. 4x plus 2y minus 2z equals 0. -3x minus y plus 4z equals -2. So it's not quite in the form that we can write it as a augmented matrix. First thing that we want to do is we want to get all the variables to one side. And so that first equation, we're going to need to add 9z to both sides. So that first equation could be rewritten as 3y plus 9z equals 0. So now let's go in and let's rewrite our system as a matrix. So our first equation, notice there's no x value. So if there's no term with the variable in it, then you're going to need to put 0 for that spot. So no x value, so 0, 3, 9. We're going to do that vertical line, and then it's equal to 0. Second equation, our second row is 4, 2, -2, 0. And the third row is -3, -1, 4, -2. So we want a 1 where that 0 is. So notice if we add row 3, plus row 2. And then let's make this our new one. Because we can switch rows around. So maybe let's just make row 2 now what our row 1 was. So let's rewrite this as a new row 2. So just swapping it. We have 0, 3, 9, and 0. Our row 3 we're using to help us manipulate and get that one where we want it. So we're going to rewrite row 3 because we're not going to change anything yet. So -3, -1, 4, -2. Okay, so adding row 3 to row 2, and that's going to be our new row 1. So -3 plus 4 is 1. -1 plus 2 is 1. 4 minus 2 is 2. And -2 plus 0 is -2. So now we have a 1 where we want it. We're going to use that row with a 1 where we wanted it to get rid of the entries below it and make it 0. So only thing we have to get rid of, because we have a 0 in the second row now, is that -3. So 3 times row 1 plus row 3. So let me just rewrite again row 1 and row 2, because those are not changing. And our new row 3. So we're doing 3 times 1 is 3 minus 3 is 0. 3 times 1 is 3 minus 1 is 2. 3 times 2 is 6. 6 plus 4 is 10. 3 times -2 is -6. -6 minus 2 is -8. So we got our first column done how we want it. We now want to move to our second column, and where that 3 is, we want to make it a 1. Notice this time, if we multiply 1/3 times row 2, everything is divisible by 3. So we wouldn't have to deal with a fraction. The other way you could have done it is we could take -1 row 3 and add it to row 2. So I'm going to do 1/3 times row 2. So my first row is staying the same, 1, 1, 2, -2. My new row 2 is 0, 1, 3, 0, just dividing every term by 3. And my row 3 is the same, 0, 2, 10, -8. So let's use this one to get rid of the numbers above and below. So if we do negative row 2 plus row 1. So my row 2 is the same. And now we're going to get our row 1. So -2, I'm sorry, not -2. We have -1 times 0, 0 plus 1 is 1. -1 times 1 is -1 plus 1 is 0. -1 times 3 is -3 plus 2 is -1. -1 times 0 is 0 minus 2 is -2. So now let's get this 2 down here to be a 0. And so if we do -2 row 2 plus row 3. So 0 times anything is 0 plus 0 is 0. -2 times 1 is -2 plus 2 is 0. -2 times 3 is -6. -6 plus 10 is 4. -2 times 0 is 0. Plus -8 is -8. So we're done with column 1. Now we move to column 3, get a 1 where we need it. And notice if we multiply 1/4 times row 3, that would make that a 1. So we got 0, 0, 1. 1/4 times -8 is -2. I would rewrite row 1 and row 2 down because we haven't changed it yet. But now we're going to use that row 3 to get rid of the 3 and the -1 above. So row 3 plus row 1, that would make a 0 where we wanted it. So we get 1, 0, 0. -2 plus -2 is -4. Now let's multiply row 3 by -3 and add it to row 2 to make that a 0. So we get 0, 1. -3 times 1 is -3 plus 3 is 0. -3 times -2 is 6. 6 plus 0 is 6. And then our row 3 is the same. So I can read off my solution. So I have x is -4, y is positive 6, and z is -2. And if I didn't do any errors, which I hope I didn't, we could check it back in here, our original system, and show that that works. So is 3 times 6, that's 18. Is that equal to -9 times -2? It is. 4 times -4, that's -16. 2 times 6, that's plus 12. -2 times -2, that's plus 4. Is that equal to 0? And it is. Check in the last equation. So -3 times -4, that gives me 12. -6, and 4 times -2 is -8. Is that equal to -2? And it is. Okay, so we didn't make any errors in there when we solved for the solution. So if you're on an exam, you can always go back and check to make sure that you've gotten it right by substituting it back in and making sure that each of the equations give us a true statement. If for some reason you're on an exam and you didn't understand or you didn't get it right, you could say, you know, I know that there must be some error in here, but I know that, and I can't find it, I don't have time or something like that. I don't know. You're going to get more partial credit showing me that, yeah, I did check and I realized this isn't working. Okay. So let me see if there's any questions. We've been looking at solving systems of linear equations, and now we're going to jump into solving systems of nonlinear equations. And so we have one system in front of us, y equals x squared plus 1, and y equals 4x plus 1. The directions told us to graph each equation in the system and then find the points of intersection. So you should be able to look at these equations and know what the shape of the graph looks like. Y equals x squared plus 1, we know is a parabola, and we can use our rules of transformations that plus 1 shifts that parabola up 1 unit. And so we have a point at, 0, 1, and then 1, 1 was a point on the original one, so shifting it up 1. So 1, 2, -1, 2. 2, 4, so that's going to be now 2, 5. And -2, 5. Okay, so we have this graph of our parabola. And now let's graph the other equation. So y equals 4x plus 1. You should notice that that is a line. It's in slope-intercept form. So our y-intercept is at 1. And our slope is 4, or 4 over 1. So if we rise at 4, we would run over 1. Or if we fell 4, we would go over 1 to the left. So let's graph that. So it looks like this graph is going to intersect in two different spots. We can see one of them right here, but let's solve it algebraically and show what we get. Okay, so there's a couple ways to solve this. We could use the addition elimination method. If we multiplied one of those equations by -1 and added it to the other one, notice the y's would go away, and we would just have an equation with x. The other way that we can do this is we can use our substitution method. So we know that y is equal to 4x plus 1. So let's just go into the equation above and let's plug in 4x plus 1 wherever we see a y. And so we have a y there. We're going to plug in 4x plus 1 is equal to x squared plus 1. So you need to identify what type of equation and how to go about to solve it. It's a quadratic equation. So in this case, it looks like it's best if we set this equal to 0. Let's subtract 4x and subtract 1 on both sides of our equation. And if we do that, we get x squared minus 4x. Our 1's are going to cancel, gives us 0. So I can solve this by factoring out in x and then setting each factor equal to 0. So we get x times the quantity x minus 4 equals 0. So either x is 0 or x is equal to 4. So that's just the x value of our point. We need to figure out what the y value of the point is. And so when x is 0, we can go back and we can plug it into either one of the equations. So if we plugged it into the first equation, we would have y equals 0 squared plus 1. So y is equal to 1. So we have a point at 0, 1, which we could tell by just graphing it that that was a point. And now let's plug in x equals 4 into one of those equations. Again, it doesn't matter which one, you should get the same result. So we have y equals, if I plug it into the second one, 4 times 4 plus 1. And so I would get 16 plus 1, which is 17. So y is 17. And so we have a point at 417. So those are our two solutions to that system of equations. So let's pull another one. What if you had x squared plus y squared is equal to 10. And we have x, y is equal to 3. Same directions, we want to graph each one of our equations, and then we want to solve algebraically for the points of intersection if they exist. So looking at the first equation, x squared plus y squared equals 10, you should recognize what that equation is. And that equation is a circle with a radius of square root of 10. So our center is 0, 0. And our radius is equal to the square root of 10, which is approximately 3. So square root of 10 gives us approximately 3.16. Okay, so let's graph that first. So from our center, we're going to go up, down, left, and right, approximately 3.1. And then draw our circle. And then we want to graph x times y equals 3. If we divide both sides by x, we could get what y by itself. And doing that, we would get y is equal to 3 over x. Or if this helps you to look at it this way, we have y is equal to 3 times 1 over x. So recall 1 over x, that was another shape that you should have been familiar with and graphing. If we graph 1 over x, it looks similar to this, where we have vertical and horizontal asymptotes at x equals 0 and y equals 0. That 3 is just making it extend faster. So if x was 1, y is 3. If x was, let's say, 1/2, then we get y is 6. And if, let's say, x was 3, we would get y is 1. So get this graph that looks like this. This is actually symmetrical across the origin. So we do have points. So this point 1, 3 is now -1, -3. That point that was at 3, 1 is now -3, -1. What other point do we have? So -1/2, -6. So looking at this, it looks like I'm going to get 4 separate solutions back. There's 4 points of intersection here. Okay, so in this case, it doesn't look like I can use the addition method, which is also called the elimination method, where I can multiply one equation by something and add it to the next and have one of those variables fall away. But we could go in and we can use that substitution method. So we already solved for y in that second equation. Let's go into the first equation, and wherever we see a y, we're going to replace it with 3 over x. And so doing that, we get x squared plus we see y, and put parentheses, quantity squared equals 10. And y was this 3 over x. Okay, so let's simplify this. So this is x squared plus, well, 3 over x, quantity squared is 9 over x squared equals 10. Let's clear our fraction. And we can do that by multiplying both sides of our equation by x squared. And so if we do that, we get x squared times x squared is x to the 4th. X to the 4th, and then we have plus x squared times 9 over x squared is just 9, is equal to 10x squared. So this looks similar to a quadratic equation. So let's get everything to one side of the equation. We have x to the 4th minus 10x squared plus 9 equals 0. We could use that substitution, or I notice that I can break this down. There are 2 numbers that multiply to 9 and add to -10 is -9 and -1 equals 0. So notice that x squared minus 9, that's a perfect square. And so let's factor that. So that's x minus 3 times x plus 3. And then x squared minus 1 again is a perfect square. So x minus 1, x plus 1 equals 0. So there are 4 values of x that set that equal to 0. So x equals 3, x equals -3, x equals 1, and x equals -1. So go back into either one of our equations and we can plug in that value for x to figure out what y is. So if we go in there and we plug in 3 over 3, we would get 1. So when x is 3, y is 1, which looked like we had right here, right? 3, 1. If x is -3, we got -1. 3 over -3 is -1. So -3, -1. And we know this too because it's symmetrical to the origin. If one thing is a point, then the negative of the x and negative of the y is also a point. If x equals 1, we plug that in for x, we get 3 over 1, which is 3. So we got a point at 1, 3. Plugging in -1, we got 3 over -1, which is -3. So we have -1, -3. Okay, so let's pull another one. In this case, our new system is going to be y is equal to the square root of 4 minus x squared. And y is equal to 2x plus 4. Okay, so again, it wants us to graph it and then find the solutions algebraically. Notice that y equals the square root of 4 minus x squared. That's actually a semicircle. If you squared both sides of that equation, this would be y squared is equal to 4 minus x squared. Add x squared to both sides, we would get x squared plus y squared equals 4. So this is a semicircle with a radius at 2, center 0, 0. It's everything that's above the x-axis. Okay, so that is this equation. The other equation is just a line, y equals 2x plus 4. And so in there, we know that our y-intercept is 4 and our slope is 2. So if we go down 2, we would go over 1. If we went down another 2, we would go over 1. So it's looking like this point, -2, 0, is where they're touching. So let's just do substitution. So let's plug in that square root of 4 minus x squared in wherever we see a y in the other equation. So doing that, we have 4 minus x squared. This is equal to 2x plus 4. So a radical equation. Remember, we isolated the radical, it's already done. And then we squared both sides to get rid of the radical. And so this is 4 minus x squared is equal to, we're going to have to distribute 2x plus 4 times 2x plus 4. Be careful because we squared both sides of an equation. If we raise both sides of an equation by an even powered, we might get extraneous solutions. So we're going to have to check. Okay, so we have 4 minus x squared. So distributing, we have 4x squared. Our middle term is going to be an 8x plus an 8x, so plus 16x plus 4 times 4, which is 16. So let's get everything to one side of the equal sign because it's quadratic. So let's add x squared. So we would have 5x squared plus 16x, and let's subtract 4. So 16 minus 4 gives us plus 12 equals 0. So I see that that's going to be factorable by the AC method. I noticed that my A value is 5 and my C value is 12. If I multiply those together, that's 60. There are two numbers that multiply to 60 and add to 10, 6 and 10. So let's just rewrite our middle term using those two numbers. I'm going to write it as plus 10x plus 6x. That's the same thing as 16x plus 12 equals 0. Factor by grouping. So pulling out a 5x, we're left with x plus 2. Pulling out a 6, we're left with x plus 2. So we have x plus 2 all times 5x plus 6 equals 0. So x is negative 2 and x is negative 6/5. So my graph's not showing it, but it looks like it's also intersecting here at -1, -1/5. But let's check. So we want to check, actually, we need to find our y value. So we have our x values. Let's find our y values. Maybe plug it into this second equation. So if we plug it into y equals 2x plus 4, plugging in -2, we get y equals 2 times -2 is -4 plus 4 is 0. So that is a point at -2, 0. Which we had already said that was probably going to be a point. Now plug in -6/5 there. So plugging that into y equals 2 times -6/5 plus, let's get a common denominator now. I'm going to need a 5 in my denominator, so we can multiply that 4 by 5/5. So that's 20/5. So this is -12/5 plus 20/5 is 8/5. So we have a point at -6/5 and 8/5. Okay, let's just make sure. If we plugged in -6/5 back into this equation here, let's make sure that we have a true statement. So let's see. So I have is 4 minus a -6/5 quantity squared equal to 2 times -6/5 plus 4. So this is going to be the square root of, this is 20/5 minus, if I square this is going to be 36/5, 20/5 actually. So actually I didn't need to change my denominator to 25. So 25 times this 4 here. So that would be 120/5. Is this equal to -12/5 plus, let's get a common denominator, 20/5. So this is 64/25. Is that equal to 8/5? And it is. Okay, so I just wanted to make sure that that was a solution because, like I said, we were squaring both sides of our equation so we could get an extraneous solution. And so it is intersecting in two spots. It's just my line doesn't look perfect. And so we have two solutions, -2, 0 and -6/5, 8/5. So these are kind of cool in the fact that it's showing me a lot of different things that we've done in this course. Like in that example, solving a radical equation, substitution method, knowing that if we raise both sides to an even power, it's squared, graphing, etc. Okay, so we have another system of equations in front of us. This just in the direction told us to solve this in any method that we prefer. We have log base x of 2y, that's equal to 3, and we have log base x of 4y, that is equal to 2. So a couple of things that we could do. We could subtract each of those equations. I'm thinking that we should rewrite each of those equations in exponential form. And let's do that first. So if we rewrote this in exponential form, the base of my log is the base of my exponent. So this is x raised to, logs are just exponents. So this would be cubed equals 2y. Same idea, if we rewrote this log in exponential form, it's equivalent to x squared is equal to 4y. So I could go and I could solve for y in this case and then do substitution. I notice if I multiply this first equation by -2, and I add it to the second equation, the y's would go away. So maybe let's do that. So this would give me -2x cubed equals -4y. And we're summing it with x squared equals 4y. So notice that left-hand side of the equation are not like terms. And so that is -2x cubed plus x squared equals 0. You notice that we can factor on x there. So this is the same thing as -2x squared plus 1 equals 0. So we're looking at when is x equal to 0? And when is -2x squared plus 1 equal to 0? So we can use our square root method. Let's subtract 1, divide by -2. We would get x squared equals +1/2 if we did that. Take the square root of both sides. We get x is equal to plus or minus the square root of 1/2. Which is the square root of 1, which is 1 over the square root of 2. We tend to not like radicals in the denominator. We could rationalize that denominator. And this would give us -1. Negative plus or minus root 2 all over 2. We're dealing with logs. We need to be careful. We can't have, remember for logs, our base. So in this case, x has to be greater than 0. Our base can't be 1 either. That's not the case. And we'll see, but we can only have log of a positive number. So this right here can't be 0. I can't have the negative root 2 because that's less than 0. And so right now, all I have is that x is equal to root 2 over 2. So we want to solve for y. Let's plug that value into one of the log equations. So we have log of root 2 over 2, 2y equals 3. So we can solve for this. Let's rewrite it in exponential. So this is root 2 over 2 quantity cubed equals 2y. Let's multiply both sides by 1/2 to get y by itself. So this would be root 2 cubed all over Well, we have this 2 cubed in the denominator, and we were multiplying by 1/2. So this is really 2 to the 4th. I can simplify this because root 2 times root 2 times root 2, that's 2 root 2 all over 2 to the 4th is 16. So y is equal to root 2 over 8 when x is root 2 over 2. Other thing we need to make sure is that we don't have a log of a negative number. Plugging in root 2 over 8 is not going to give me a log of a negative number, so I should be good. Okay, so our next example, 4x squared plus 3y squared equals 4. Second equation is 2x squared minus 6y squared equals -3. I notice if we multiply that first equation by 2 and sum it to the second equation, the y squareds would go away. So let's multiply this first equation by 2. And if we do that, that would give us 8x squared plus 6y squared is equal to 8. So let's sum these two equations. Doing that, we get 10x squared is equal to 5. Divide both sides by 10, we get x squared is equal to 5/10 or 1/2. Take the square root of both sides, we get x is plus or minus the square root of 1/2, which we just showed was the same thing as root 2 over 2 by rationalizing the denominator. So we have two values of x, and we want to figure out what y is. And so we want to go back in and plug it into one of our equations. So let's do it the first one. So we have 4. We see an x there. Notice that when we square this, it's going to give us the same result if I put that plus or minus in here. Plus this 3y squared equals 4. Right, so 4 squaring square root of 2 plus or minus, that's positive 2 all over 2 squared, which is 4, plus 3y squared equals 4. 4's cancel, we can subtract 2, so we have 3y squared equals 4 minus 2, which is 2, divide by 3, so y squared equals 2 over 3. So y is equal to plus or minus 2 square root of 2 over square root of 3. We can rationalize the denominator. So we get y is plus or minus root 6 over 3. So we actually have 4 separate solutions. So if we had positive root 2 over 2, we have a positive root 6 over 3. Positive root 2 over 2 also gave us negative root 6 over 3. We have a negative root 2 over 2. That's positive root 6 over 3. And negative root 2 over 2 and negative root 6 over 3. So that kind of makes sense. We would have had an ellipse, right? And a hyperbola. Let's see, is that hyperbola is going to be this way. So it's going to look something like this, where it's intersecting in 4 different spots. Okay, so we're going to stop here for today.